Hello, this is Alazi Alosain Kebe, and once again, it is my pleasure for us to continue our demonstration video on AquaCrops, a crop water stimulation models created by FAO Lands and Water Resources Department. And the last time we basically do some demonstration on this AquaCrop software, and we do the climate models and how we can stimulate the climate. And we will not go detail to that today, because what we are basically going to do today is for us to work on the soil profile. We know for climate for the climate file or the climate section, what we basically do, we first create the climate file using our own recorded data. These data, we record them, we transfer the data in Excel, and from Excel we convert these data to text file, and in text file we are able to create our climate files, and we display our graphics, our graphs in that previous video. The video is in the link and you can watch that video. And we also do another video where we pre-install we use pre-installed climate data. The pre-installed climate data, we use this pre-installed climate data for us to generate our simulation. And in doing so, what we basically do, if we want to use the pre-installed climate data for us to run our simulation, we go here, we say select climate file. There are several pre-installed climate files that are already here. We can use any one of these for us to do our simulation. That's we have to do our own practice without having our own data. Let's say example, we use this Cordova. We use this Cordova, or say we use the Foggia, Italy. This is a meteorological station in Italy that have recorded the climate data from January 2000 to 31st December 2001. These are climate data. We can select this one. Let's say we select this one. After we select this one and we go, that means it have already been selected here. You see, in the climate section, it have been selected. What we basically do is that we default crops generics, and also there is a default crops here. We are not discussing about the default crops, but let's go to soil profile. Here we click on soil profile. We click here, create soil profile. When we say create soil profile, here we can use the pre-installed soil parameters. These ones are pre-installed soil parameter. We go back again. Let me show you. Here, the soil profile here, this pre-installed soil profile, if we go here, the soil profile, they are already default. The default soil profile is deep loamy soil. Deep loamy soil. This deep loamy soil, if we click here, display or upload soil profile characteristic, if we click on this one, you can see here the descriptions. The file name is default s.sol. These are the saving, how we save this. We sell in climate, we save it to text txt file. Now for soil, we save it with sol file, and the description is deep loamy soil. Deep loamy soil profile. And this one, we can go to check the characteristic of it, and with number of soil horizon is 1. You can see number of soil horizon. The description is that loamy soil horizon, and the thickness of this in meter is 4.0 meters, and the TAW, that's the total available water, millimeter per meter per each millimeter. There are 200 millimeter per each 1 meter of this soil loamy soil horizons. And you can see here the soil water, and we talk about the retention section. Here we have the PWP, that's a plant available permanent wilting point, permanent wilting point. And we have the FC, we have the field capacity. All of them are in percentage. We have saturation point, the soil saturation point, which is 50. This is 10, 30, 50, and we have a perfect loamy soil horizon here. Hydroelectric conductivities here. Also we have these figures. All of these figures, we can alter them, we can change them based on our own soil analysis. our field soil analysis, the soil sample we have collected from the field, we can alter all of this one. We can alter this one to 2, and when we alter to 2 soil horizon, you can see here, because if I know all of us will have studied the different horizon, the A horizon, the B horizon, the C horizon, and the D horizon, up to the O horizons of the soil. But if we consider only 2 horizon here, you can see here, as the thickness, as the soil horizon go down, the thickness decreases. You see the thickness here is 4, this is 0.1, but the total available water still remain the same, and you can see all of these parameters remain the same, but you see that the thickness of the soil decreases. Now we can alter any of this, but we can still remain it with the default. We left it with the default here, and we can plot these parameters. These are the soil parameter we have analyzed, and we have put the figure here. We can plot it here to see how it look like. Loamy soil horizon, you can see here the capillary, the hydroelectric conductivity sector. Here you can see all the porosity, fine soil fraction. It is a very perfect soil for most crop cultivations. For most crop cultivation, this soil horizon is the best, and you can see even the retention here and the volume, everything is perfect. But for some crops, it is not the ideal. We need a better soil profile for it. Let's say if you are working with rice, even though loamy soil is very rich in nutrients, loamy soil has a high porosity levels and etc., but the water retention compared to a clay soil is very less. That's why for rice cultivation, for rice crop, we use clay soil, because clay soil has a higher water holding capacity compared to this loamy soil. And we know rice is a hydrophilic crops that they love water. They are water loving crops, and you can see the surface area of it as well here. The B horizon, you can see from the B horizon here, the default curve number, because curve number is also very important. It determines the hydroelectric soil groups here, also based on the K-SAT on top horizon, and the property is very, very important. We can alter this one as well. You can change it from 60 to 46. You can change it from 60 to 50, depending on your what parameter you have got from your lab experiment, or which stimulation you want to try. You can try different stimulation. And readily evaporated water, readily evaporable water, REW is 9 here, 9 millimeter, while the default value is 10 millimeter, which is the ideal one. But for this soil parameter, 9 is the ideal for the soil parameter, because we are working on loamy soil here. And we can check the capillary rise as well. In the capillary rise here, rooting zone, we can see the rooting zone here. Because this soil is a loamy soil, we know it is the ideal soils that basically it's very good for that of vegetable production. If you want to produce vegetable like cabbage, you want to produce like these tomatoes and etc., loamy soil is very recommended for garden soils if you are working in gardens. But for field crops, it is not most ideal for most crops, because most crops are either water loving crops, or most crops they do not like too much water, and loamy soil can retain more water. Like for groundnut, we cannot pure loamy soil is not good for groundnut cultivation, because it can attract a lot of different things. And sandy loam will be very nice, and we'll discuss that one later on. And the capillary rise here, we have discussed all of this. And after you have altered any of this parameter, before you can leave this one, you have to save it. Because you have altered them, and you save it. And when you are saving it, you might save it with a new name. Let's say example, I have altered, but I have not do any alteration. Just try to explain some features here, some menu here, and maybe I say it Kebe P1. Kebe P1, that in Kebe practice 1, just explanatory, and I save this one. After I save it here, you can check the names section here. In the soil profile, it says now Kebe P1. .sol. This is our soil parameters, and we can, for us to see if there is a change in this one simulation. Let's say we run our simulation. We go to simulation, and when we go to simulation, one thing you have to observe here, you will see our ET naught is 2.6, and rainfall and all of these are default, and we can start our simulation. Let's see with the this climate data and other things. You can see here our simulation here. We can see we have the almost perfect, not perfect, because you can see from this end here, this is the canopy cover. You see there is a perfect canopy cover here from the start, coming down, but from this, after flowering, 100 days after sowing, and the canopy started going down. And for these crops, the canopy do not mature as well. You can see some of the reason why the canopy do not there is no perfect canopy here, or the perfect development of the crops. One of the reasons that's very important in the crop is the water, the plant available water. The plant available water here, you can see the field capacity. This green line is the green line here is the perfect line for us to get a perfect canopy and perfect evapotranspiration level. But because you can see here, the water, the blue one is the water here, and you can see here the blue one is the water here. The green one is the field capacity area. It is the plant available water that is available to you during these stages from sowing up to around 40, let's say up to around 30. There was a perfect water here. The water was very nice, but what happened is that the water started decreasing, and the canopy, at the end of the day, the plant do not reach its perfect maturity according to its simulated pre-simulated area. And thank you so much. This is one part, and the second part of this demonstration will be going on, because for us to limit our recording. Thank you. Oh my God.